All right, hello everyone. This is lecture 14. We're going to be talking about push notifications, which is necessary for homework 5 when you're implementing that social media platform. I do want you to implement some kind of push notifications to notify users when they have new content they should be reading or whatever. Last time I gave a case study of architecture showing the National Gun Violence Memorial architecture, going into some of the details of the billing, how much it costs to run, what it would take to scale it up to the size of CNN.com. So this is an article publishing system essentially. So it's pretty similar to Wikipedia. The architecture that I designed is pretty similar to Wikipedia. We have caching on the front end and load balancers and a stateless application to generate pages. And then on the back end, we have a SQL database with read replication for when we want scale. We also have some media files, in particular photos, and those are stored on the S3 file store and made available publicly. So very similar to Wikipedia, but I just had more numbers in terms of the actual, because I operate the site compared to Wikipedia. So I hope that was useful. Today, though, is a new topic. Although this is really continuing from the previous discussion on message queues when I talked about asynchronous processing. So this is about asynchrony in this between clients and messages they received from servers. Okay, so nowadays, of course, client devices are mobile, right? And we compute on our smartphones, and we expect the services we use to be kind of like, we kind of are using them all the time, even when we're not in front of the computer, right? So if you're a Facebook user, you're kind of always on Facebook in a sense that you always are there and someone can always send you a message, right? And even if you're not using the application and requesting an update, you need some way to get that update. So we've showed so far how REST APIs can define the way that programs interact with, the way that services interact with each other, and they allow services to define how clients make requests and get responses. So we've designed systems where the client makes a request of the service gives a response. Push notifications are about reversing the role of client and server and allowing the server to generate a response, essentially, or a message, let's say, for the client, even though the client didn't ask for anything in return initially. So what we kind of want is a way for the server to send a request to the client, right? Instead of the client sending a request to the server. The way the internet is designed and the way these client devices are designed, doing it in that straightforward way is not possible. We can't really have a client implement a REST API because those clients are not easily reachable in the same way that those backend services are. So a bunch of reasons for that. So first of all, those client devices are not always on. So if we're talking about a smartphone, the power could be off, you could be out of service, you're moving around, and that means that your IP address changes, and you don't have a DNS name that always points to you. So this is very different than servers. Servers are always in one location, or at least they're you can have IT staff or DevOps staff reconfigure it, but you have to, at any given moment, you have your service reachable in a consistent location. Those devices also are might have a firewall running to prevent them from being hacked, right? So they're not really designed to run services in the same way that backend applications are designed to listen for these kinds of network API requests. So the way we've designed systems so far, we have, because of these limitations and the fact that really it's just these backend servers that are running in data centers that are always on, we kind of have tried to design systems as much as possible to rely on clients making requests and servers giving responses. When we do that, the server only does work when the client asks it to, so the server actions are synchronous with the client. But we saw later on with message queues, for example, there might be times when we want the server to do something in the background, and maybe when it's done, we want it to send something back. So that's one use case for push notifications. Or we could have a system where other users' actions trigger different users to want to receive data. So if someone sends me a message, I should receive that on my device, regardless of whether of anything I've done, without me doing anything first. We don't want users to have to like check their messages to get a message. Okay, so we have a network. We have devices that are not really designed to listen for, or the clients are not designed to easily get messages, and somehow we have to build some hacks to get around this to allow clients to allow servers to notify clients, and that whole class of solutions is called push notifications. All right. So we're going to be talking about both smartphone and web browser notifications. They work slightly differently, although there's some commonalities between them. So with smartphones, the challenges, like I mentioned, are that they're always moving around and they're getting different IP addresses as they move around. So IP addresses are like the numeric locations on the internet that allow devices to be reached. The way that this is solved for both iOS and for Android is that Apple and Google, respectively, depending on the OS, run a push notification service that handles delivering push notifications. So instead of having, the reason for this is that we want some kind of location registration, a central location registration in one place that can be leveraged by all the apps running on the phone, right? So when your phone moves around and gets a new IP address, if you didn't have this push notification service, the phone would have to notify all the different apps it's using that might want to send it a push notification of what the current new IP address is. So as you're moving around throughout your day, your phone might be sending, every time you move a little bit, to a different location on the network, and you get a new IP address. You could get a new IP address. You don't always, but you could. And when that happens, your phone would have to like would send messages to like dozens or even like hundreds of different apps that you have installed, so that they all would be able to send you a message. Even though very likely they're not going to do that individually. Usually push notifications are rare, but when they do come about, the apps. The app operators do want to be able to reliably deliver those messages, right? So what location registration does is it has the operating system, whether it's iOS or Android, be responsible for being the intermediary to deliver push notifications. So whenever any one of the apps that's installed on your phone wants to send a notification to your phone, it actually sends it to the operating system operator. So like it sends it to either Apple or Google, to either the Apple Push Notification Service, APN, or the Google Cloud Messaging System, GCM. And whether it's iOS or Android, it sends it to one or the other, and then that system should have a record of whatever your latest IP address is, and it should also have a persistent network connection open already between your phone and that service, and it can actually deliver the message on your behalf. So as an app developer, I don't actually deliver notifications directly to smartphones. I deliver them through Apple or Google. Okay. So the way that works, though, in order to give users control over which apps are allowed to send them push notifications, there's a registration process. So the phone will actually, the app that you're using will prompt you to ask you if you want to allow push notifications, and if you say yes, the app will make a request to the push notification server and ask it for an ID for that user. And then that app can store that ID in its database and later on use that along with any message it wants to send on the back end. So if the let's say Snapchat has a message that wants to deliver to you, it would need to know your user ID on Apple Push Notifications or Google Cloud Messaging, and it would send its message along with that user ID to that service, and the service, Apple or Google would deliver it for them. Okay. And these phones have a persistent connection, one persistent connection to either one of these services to make that delivery possible. If you took CS340, there's a little, I guess it's really not worth getting into this detail, but if you have a private IP address and you're behind a NAT, what your phone actually will keep a persistent connection to one of these servers using by sending messages periodically, and that allows the messages to come back in the reverse direction, even though you have a private IP address. All right, but that's really not too important, and that's a networking detail. But the way this works at a high level, we'll just look at three components working together. Right, we have our backend, we have our smartphone app, and we have the push server, which we don't run. So keep in mind that two of these are actually managed by us, the app developer, but they're not the same application, right? One of them is running on our backend in the cloud. The other is an app of ours that we coded, but that the user has downloaded and is running on their smartphone. And then this third party is either Apple or Google. Okay, so the phone has a connection to this push server all the time, and as it moves around, it makes a new connection. When it moves around, that connection is broken because the IP address changes, but it makes a new connection every time it connects to the network, and this push server keeps track of where this particular user is at that time, so it can deliver messages on behalf of all the apps. So the app, when it wants to send a message to this user, it actually has to send it to the third-party push server, whether it's Apple or Google, and then that push server will deliver it to the phone through that connection that the phone is keeping to the push server. The phone is not keeping a constant connection to the app server. It could do that, but one of the reasons it actually is not feasible to do that is because smartphone apps are designed to there are limited resources on a smartphone, and I know that for iOS in particular, it's not possible to run background tasks all the time with your app, right? Your app would be rejected from the App Store if it did that. So when you leave your app, like when you go to the home screen, your app actually stops running, is not running code. It cannot actually listen for network requests from your app service. You cannot send even if this did have a public IP address and you did make a connection and you sent keep alive messages through the NAT, that would only work while the app was in the foreground running on the screen. Once the app turns off, it's only the OS itself takes care of keeping just one connection open to Apple or Google for the purpose of delivering messages, and this is an efficient way of doing it, so it doesn't waste power. It doesn't have a bunch of apps keeping connections to all their individual servers. Okay, but there are a few steps that the app has to go through to make this work. So initially, the app is installed, and so me as an app developer, I don't have the necessary information to send a push notification to this user. What the user has to do is launch the app, and then some code in the app on the smartphone will make a call to the OS to register for push notifications. That will cause the OS to throw up a dialog on the screen that asks the user their permission to get push notifications. If they agree, then the push server, a request will be sent to the push server by the OS, and the push server will give back the application an ID, which says to me as an app developer, okay, you can now reach this user through the push notification service and use this ID to contact them. This ID is permanent. It's not like an IP address which changes over time as the user moves throughout the network. This is like a number that identifies the user, and of course there's a database in here that will track the mapping between that ID and the IP address as the device moves around. When the smartphone app gets that ID, it has to do something with it. Now, in the end, what's actually going to need that ID is the backend server. So what the app has to be coded by the developer to return that ID back to its backend, and the backend has to store it in a database so that later on, after much time passes, let's say that some other user in the system has sent a message to you. Now, your backend wants to notify this user that you have a new message. This phone is off. It could have dead battery. But in general, let's say the app is not running. So there's no way the app can send a message to the user. We don't want the user to have to open the app and guess that there's a message and check for it. But what this backend app can do now is send a message. That's the payload to the push server. In this case, it is Apple or Google, with the ID that it got before that identifies this particular user, and then the push server will send the message, even though the phone's in background mode, to the app, and then you'll get on screen one of these like push notifications. And if the user clicks it, depending on the content of the payload, it'll do whatever is coded in the payload. But most likely it'll just launch the app. Okay. And then when the app loads, then you would actually fetch the contents of the message through the normal REST API means. But that was a way of getting the phone to do something, even though it wasn't running, and even though it didn't have a network connection that we knew about. Right. The only thing we knew about the smartphone was the ID that the smartphone app got by registering for the push notification service in step 1. And 2, we got back the ID, and they gave that back here. So both the cloud database keeps track of a mapping between the ID and the current IP address of the phone. The phone keeps the OS in the background keeps a connection to this push server so they can receive these payload messages, these push notification messages that are labeled as payload here. And the app server has to store in its database the IDs for the devices that should be notified. Okay, and we'll show that later in a second. So that was smartphone notifications. And it works basically the same for iOS and Android. Web browsers also have this problem because browsers were designed to pull data from servers. They were designed to have users type in addresses, fetch that data, and then the JavaScript runs and sometimes gets additional data, does posts or something. So we have servers that implement REST APIs. Browsers make REST requests to fetch data, but the browser, again, cannot implement a REST server to respond to requests for many of the same reasons. You don't have a public IP address, and it would be kind of a security risk. It would make the clients kind of like hackable in a sense, I guess. But okay, anyway, we want browser applications also to get pushed updates from the service, even though we don't have quite as many problems as a smartphone. We don't have the same resource constraints. We don't have the limitation that the code stops running when it gets backgrounded, but it's still nevertheless is somewhat difficult to get push notifications because the IP address could be private and browsers are just not designed to open to listen for requests. Browsers are designed to make requests and to handle the responses. So one way of dealing with this is polling. This is where you design your web application to just periodically ask for new data. So every 5 seconds, let's say, make a request and ask if there's new data. That can kind of work, but it's not a great solution because you have this trade-off between latency and network overhead. Either you're asking a lot and you're just sending all these wasteful requests, or you're sending once in a while, so there's not a lot of overhead, but then you might have to wait a long time before you see an update, right? So the modern solution to this problem is to use Websockets, which are kind of like a TCP socket, if you know what that is, that the browser supports. So this is like a long-term connection you make to a server that allows messages to flow in either direction. It's not just like an HTTP style interaction where the client makes a request and one response comes back. You could get a response later without prompting the server through a WebSocket. Okay. So polling is one solution. Long polling is another answer. It was another old solution prior to WebSockets. I'm not going to talk about it, I guess, because WebSockets are superior and well supported nowadays. All right, so the way WebSockets work is that the client has a long-lived bidirectional network connection to the server. It's similar to a TCP socket, if you know what that is from networking class. But unlike a TCP socket, it's a WebSocket is available in a browser to your JavaScript code. Okay, so like TCP is actually a very low-level kind of API. So you can build a bidirectional network connection if you were coding in Java or Python or something, but for code that runs in a browser, only recently with the standardization of WebSockets has it been available to create a bidirectional network connection. So a JavaScript app can do that. It can set up one of these WebSockets, and this allows clients to send API requests through the WebSocket. Basically, you send a JSON message to the server. The server can respond with a JSON message at any time, though. I mean, it could be in response to something you sent, but it could be unprompted. You could send one request and get a response from the server, and then get another response from the server, and then 5 minutes later get another response from the server, because that socket is kept open indefinitely. It's permanently, let's say. the connection is not just for the one request and response, which is normally how REST APIs work. You set up a connection, you send a request, you get a response, and the connection is closed. That's because it's a client-server interaction. You don't once the server gives you an answer, you do not expect any further answer unless you make another request, right? So WebSockets changes that and allows the connection to remain open. It allows the server to send data anytime it wants, which now like solves this problem of push notifications, right? The server, if we have one of these WebSockets open, the server can decide, at any time to send us a message, and then our web application can, react in the UI appropriately. Okay. There was an old, actually, I guess I do have a slide on the old solution, which is called HTTP long polling or Comet, which is basically the same thing, except it emulated this persistent connection by making a series of long HTTP requests. So what you would do is the client would send an HTTP request without any real, kind of like an empty request, and the server would not give a response. It would actually just keep that connection open and wait to give a response. And the reason it was waiting is because it was waiting until it might have some data available. So it could wait, let's say up to 60 seconds before giving a response. After 60 seconds elapses, it might give a timeout response, and the client would say, okay, I made a request with no data. You told me after 60 seconds that it timed out, so I'm going to make another request. And it's kept going on. Now, at some point, the server has something it wants to tell the client. And thankfully, because the client has been making these kind of dummy requests, there is actually, at that moment, there's always some request that is in the middle of being timed out, So the server can find a connection that a request that was previously made that hasn't been responded to. I mean, nothing, the request, there was no request really, it was an empty request. But you can use that empty request to give a response when it's appropriate. Okay, so the client initiates the request, but the client isn't actually making a request. It's just a request saying hey, server, if you have data, give it to me. And by the way, there's no rush. I will wait for this response up to 60 seconds, which is a long time in computer time. And eventually, if you decide to say nothing, I will ask you again immediately. And again, so this allows responses to be sent back from the server to the client at any time. And so it's essentially like the server making a request of the client, although technically from an HTTP perspective, it was the client that made the request. And that's why it works. Okay. So it's kind of, it's hacky, but it works. And there also are periodic gaps in service. So when there's a timeout, there's a little bit of time during which you have to wait for the next request to send that response from the server. So HTTP, WebSockets kind of clean this up and let servers send data send requests to the clients essentially in a clean way. All right, so HTTP, let's just do a little, this graphic shows a comparison between traditional HTTP and WebSockets. HTTP is half duplex in the sense that the requests always have to come from one side. There's always a clear client and server, whereas with WebSockets, a connection is established and then messages can flow in either direction. So instead of a request-response pattern, it's a bidirectional messaging pattern. You have to use these with HTTP. You have to use polling or some kind of long polling to hack server pushes. With WebSockets, it's built in because it's bidirectional, and the only advantage really of HTTP long polling is that there's more support for clients going back longer, but modern browsers do support WebSockets, so we can kind of rely on that for new applications. All right, so regardless of which one of these push notification technologies we're using, regardless of whether we're talking about smartphones or web applications, there's a challenge here in that the client is connected to one. The client is has one connection to the service. There's one network connection the client has made because, I mean, we haven't changed the fact that the clients have special properties, that they don't have permanent locations, that they don't have public IP addresses necessarily. So the client needs to have some kind of pre-existing connection to somewhere if it's going to be sent a message unprompted. But that connection is only to one machine. So so if we want to send a notification to the client, we need to find the place on the back end where the client is already connected and route the message through that connection, right? So because of the scalable system, we have this big distributed system where messages can originate from all over the system, yet we need to somehow funnel those messages to the one place where the client is connected. Now, in the case of Apple push notifications and Google Cloud messaging, that's kind of taken care of us. That the purpose of that service was to take care of this problem for us. You know, my iPhone would be connected to one of the many instances that Apple has in its service for push notifications, and then any app can send the request to like their load balancer and then they'll basically do a lookup in the database to connect it to the right instance that I'm connected to. Because this itself is kind of challenging, often notifications are a separate microservice, so you don't have to mix in these concerns of push notifications with the rest of your application. Okay, so I'm showing here, it's a little bit sloppy, but this is, in the middle here, I have a notification microservice. The only purpose of this is to do notifications. And on the bottom, I have other services in my system that might generate messages. So this could be this could be batch processing jobs, or like invoicing, or in a social media app. This could be these could be services that handle creation of messages and creation of content that users want to be notified about. Whenever we want to do a notification, we generate a notification, and we put a user ID label on the notification and send it to the service, and let the notification service take care of all the details. There are a lot of details there to figure out, because we don't know whether the user is on an iPhone, an Android, on iPad, on a web browser. Maybe they have none of those things, but they would like to get notifications over email. That wasn't included in the picture, but you could think of email notifications as being part of the notification service. It would be nice to have one API endpoint in this microservice that takes care of notifications to a user. And I have this defined here, like post/notification/user ID, and then some JSON notification body that is following a format that my system understands. And regardless of whether the user is on any of those platforms, somehow that notification body is delivered to them. So this microservice would take care of that. And in order to do that, it has to integrate with Apple and Google, and maybe an email SMTP server. And it also has to probably have the ability for clients to connect to with Websockets to it and deliver those messages. All right, so what this picture is showing is this really bad drawing of a phone that's connected to, in this case, Apple push notification service. That phone, just like I showed earlier on, the phone once Apple tells the phone app what its device ID is, that device ID has to be given to us, to our backend, so that we store it in the database. So later on, when a request comes in to notify that user, we can check that and then use the device ID, send the request over here to Apple so that it can notify the device. We also have clients that are connecting with WebSockets. We have lots of clients, so we'd have to have some kind of load balancer to connect the client to one of many different copies of the notification service. When it does that, that information about which machine it's connected to has to be stored in a database, so that later on, when we want to send a notification to that user on a laptop, even though the request comes in, let's say on this first instance, there's no WebSocket from this instance to the client, but there's to the laptop, but there is a connection from this fifth instance to the client. The notification service can check the database to find that location and then send another request to the right instance using the particular IP address, not using the load balancer, the generic load balancer, to get the message to the user. All right. That was a lot, but I hope that makes some sense. To make it a little bit more clear, I'm showing an example of what might be shown in a notification service database. So I have two users, and they're accessible they can receive push notifications in different ways depending on how they're using the app. Alice has an Android phone, and since she's run the smartphone app and approved notifications, that caused the smartphone app to send a message to the backend to store this particular device ID here for this user. And I can use this device ID if I send a message to Android, to Google Cloud Messaging with this device ID. Google will then deliver the message through push notifications to Alice's phone. Okay. Same thing's true with Steve through iOS, Apple push notification service. Different ID, of course, for Steve's particular phone. And these IDs were generated by Google and Apple, respectively. Steve also has two other devices, which are two browser tabs. They're actually browser tabs in the same computer. You notice the format I'm storing here is first I'm storing the notification server IP address. So these are two different IP addresses, but they're similar. Then I'm storing the client IP address, and I'm storing the client port number. This will allow the push service to find. So if I want to send a message to Steve on this WebSocket that he has set up on this first browser tab, I have to get the message to the particular server that browser tab is connected to. And that's this particular instance. So I have many clones of the push service because it's a scalable system, but this is the one that Steve is currently connected to. And then these other second two numbers allow that app server to identify which of the many network connections it has is the one that Steve's on. So this is the client IP address and the client port number. Don't worry too much about the details, but that identifies to this software running on this machine which connection is the one that it identifies the connection among the many different browsers that are connected to that machine. But you notice that Steve also has a WebSocket registration and notification database for it has two WebSockets, actually. And these are for two different browser tabs. They're the same machine because the client IP address is the same. It's a different port because it's a different connection from that machine. And it just so happens that second browser tab ended up connecting to a different instance. So if you look at the original picture, notice there are many instances of the notification service. That would be like the laptop being connected to this one, and also another tab in the laptop being connected to this other one over here. That's fine, and that's what you would expect. But when a request comes in to notify Steve, what needs to happen is this. So it could be one request like this to post a notification to Steve's user ID. That API, the implementation of that API notification service would check this database to get those three entries. One of them would tell it the device ID it needs to send to Apple to send a notification to Steve's phone. The other two, though, would tell it which of these instances it needs to send requests to tell them to relay the message through the WebSockets that they have connected to those client browsers. Okay? So that's how that works. There also is, on AWS, there's an API gateway which handles WebSockets automatically in a pretty nice way. Using lambdas, which are serverless functions, which we haven't talked about yet. But I guess just keep in mind that if you want to go to implement WebSockets, Amazon's API gateway has some features built in for handling that pretty easily without you having to implement your own notification service. Like I was showing here, basically in this slide and this slide, how you would build your own notification service and what the database would look like for it, and what API endpoint you would build for it. On AWS, you can use a combination of API gateway and the simple notification service to kind of get that off the shelf. All right. So that's it for push notifications. I hope that should be enough to do the homework assignments. I'm going to spend a few more minutes now talking about coming back to the Twitter example because it lets us talk a little bit more about architecture. I have that example prepared. So remember I showed before how Twitter used asynchrony, like there were some queues in this architecture to allow the front end to proceed, the user interface to proceed quickly, even though there was some deferred work for publishing tweets. And there was even more additional deferred work for doing notifications. So there were 2 queues here. I showed that originally there was you could design Twitter with a relational database that did joins to build feeds, but this design is better because it makes reads faster although writes are slow, right? So this is a way of dealing with the slowness of writes by deferring the work of writes and breaking it into little pieces. Okay, I'm going to show here how the how both the reads and the writes work with the NoSQL implementation of the feed database. Okay, so what we're trying to do here with writes is duplicate each tweet to all the followers, and each follower has a feed that's stored in a NoSQL database, and this publication service needs to update all of the followers' feeds. Okay, when you get your own feed, it's really easy and fast. And that's why the system is designed this way, because most of the work that Twitter does is giving feeds to users. Okay, if we have them pre-built and stored in the scalable NoSQL database, then when a request comes in to get the feed, all this API has to do is first do some authentication. So first check to see whether the request, authorization information in the request matches a real user. So some kind of auth token or API key, depending on how you want to think about it, which has to be checked with a database. That information could also be cached in like a Redis database or something. Once we are satisfied that this is a valid request from a user, then we take that user ID and use it as a key to get the feed from this NoSQL database. Okay, we get a JSON object back, and we get some data back, and we maybe build the appropriate JSON object to match the API and return it back. Okay, so here's an example of what that returned JSON look like. It's a list of tweets that have authors and text and just a bunch of them, right? This was scalable because that NoSQL database is a shared nothing architecture, and it can use hashing to split up the data, to partition the data in a way that clients can easily find a particular partition. The data can be evenly balanced. Every request involves only one or a small number of replicas among those many nodes in the database. And I'm showing a picture here of a ticket booth scenario. So this is if you need to have a bunch of, in the real world, when you have a bunch of users that are showing up at a state fair, like thousands of people, and they all want to buy tickets, and you might start off with one ticket booth, but then the line gets really long. If you want to make that scalable, right, the simple way to do that is just add a bunch of ticket booths that operate in parallel. And you can always make more ticket booths to handle more traffic. The reason this works is that horizontal scaling works because there's no coordination necessary between these ticket booths. And every user that comes in can be equally served by any one of these ticket booths. And that's the same thing for these distributed share nothing NoSQL databases. Right? So we get perfect scalability, just like the ticket sales here at the state fair. So here is how you can think of the feed database, right? The keys are the users, the values are a list of tweets. Every key maps to a set of maybe 3 replicas that store that data. But we can add lots of users and add more nodes to make the database nodes to make the system bigger, and there's no central bottleneck at all. Okay. Notice that writes, whenever there's a tweet, that tweet has to be copied to all the followers. So we have to find a list of all the followers, and then for every one of those followers, we use that as a key to look into this NoSQL database to get the feed, and then we have to add to that the new tweet, right? So that's a slow process if the user has a lot of followers. If there are a few followers, it's not a big deal, but if there are a lot of followers, it's really slow. That's why we had the queuing in the design of Twitter to let the updates of all these like thousands or millions of rows happen in the background, okay? If we used a relational database, it would be easy to do writes, because we'd only have to write the tweets once, and then we could use a relational design where there was a table that listed followers, and then we could do joins between users, followers, and tweets to build out your feed. So if we're looking at building out my feed, right? If I'm user 25, then my feed can be determined by looking in this follows table and finding all of the people that I follow. So I think this is showing follower. Yeah, so this is showing that I am the follower of 3 people. So I need to take these numbers 10, these users 10, 3, and 325, and look up all their tweets in the tweet table and stick those together to build my feed. So this is efficient because tweets are only in one place. It's well structured. It's logical. But reads are slow because it involves doing a join of these 3 tables. Okay. Notice also that if we want to build a system to be large and scalable, we want to divide this data into many different database nodes. And we'll see this creates a problem because there's no way to partition the data in a way that doesn't kind of randomly, that doesn't require me to check all the nodes in the database to get the tweets that I should see, right? We want, for scalability, we want the joins that this is doing to involve only a few database partitions, because if every database partition is involved in every request, then it will not be scalable. The system cannot handle that. There are too many requests per second for all the any one database node to handle all of them. If we were going to do that, we might as well just have one database node. Whoops. If there was some way to you could think about sharding the system in a way, partitioning the data so that we kind of had different sections of the data that could be queried to handle different users. The problem, though, is that this follows relationship creates kind of a random graph across the system. So it's true that you can put me in one partition. We can call that partition 1 and label it green. And you can put the record of who I follow in that same partition. That works fine. But once you go to the tweets of the people I follow, if we were to assign those to the same green partition, then that means that that would make the access for me fast, right? I would be accessing just one database partition. But for anyone else who follows that user, they would have to also be in the same partition, right? So to make these requests, these joins involve only one or a few partitions, everyone who is involved who sees these tweets has to be in the same partition. If we take the combination of the kind of translative relationship of those follows, there's no way to do that without putting everyone in the same partition, and then we lose scalability. Okay, I think I kind of already explained this before. But the reason I bring this up is because I want to talk about about a hybrid solution here that is kind of in between a relational design and a NoSQL design. Okay, so this random graph here shows kind of what the Twitter follower relationships are like, and the point is you cannot partition this data. We saw it early on when we were talking about that data partitioning task that we wanted to do a balanced bipartite partitioning of this graph that had few edge crossings, but that's impossible with human relationships because these graphs are kind of random. All right, so we have two basic designs that we've talked about so far. So this is the new part. Okay, so this is what you really need to pay attention to. We had the relational design where writes were simple and fast, but we could not handle a lot of data because we were using a relational centralized database. And also, reads were slow because we had to do joins. Pre-building the feeds allowed us to use NoSQL, which gave us more scalability. We could use NoSQL because we could put all of a user's information for reads in one place. Now, there was duplication there. And that duplication actually is what allowed us to partition, actually. That went hand in hand. all of the tweets that I see are in one place, but that includes tweets that are duplicated elsewhere for other users. Okay. Writes are slow. When someone tweets, it has to be copied in many places. All the followers need to get a copy of that tweet. So we're wasting space. And also for celebrities that have millions of followers, it's going to be really slow. There's also going to be a lot of wasted space for celebrities because their tweets are going to be duplicated millions of times. Okay. We saw that queuing solved some of this write slowness by allowing the user to proceed, allowing the user interface to proceed while having the publication happen in the background. But there still is a problem here. Even if we allow it to happen in the background, we don't want tweets for celebrities to take a really long time in the background while millions of entries are being updated. And we also don't want to do all that work if we don't have to, right? So for celebrities, we're wasting a lot of space, and we have slow updates. And in some sense, this is bad because our most important users are having the worst experience, right? Celebrities should have we don't want celebrities to be have delayed postings compared to regular users, right? Generally, people we want to keep those users happy. We want people to see what the celebrities are doing on Twitter anyway. That's the Twitter value proposition. So I want you to think about how Twitter can get the best features of both of these designs. So for Twitter to get scalability that the pre-built feeds give, but to not have duplication and slow writes for celebrities. So in particular, so we notice that the relational design works well for writes, but bad for reads. The pre-built feeds design with NoSQL is scalable and works well for reads, but does not work well for celebrities that have lots of followers. So try to think for a minute about solving that problem, about getting the best of both worlds here. It's pretty difficult, but think about it and see what you can come up with, and then I'll show you. Okay, so I hope you thought about that. The solution is a hybrid design. Okay, I guess you could have seen that in the title here, but what that means is hard to figure out. Basically, what we do is we have two classes of users, right? We have our normal users and we have our celebrity users, and we store their data differently, right? That's the key. For most users, we use the pre-built feed model, where so if I tweet, I don't have a lot of followers, it's okay to duplicate my tweets in, let's say, I don't know, 100 different followers' feeds. That's not a ton of work. That's 100 copies, okay? But for a celebrity, we treat them differently. For celebrities, we actually go back and use the relational design, because the relational design makes writes efficient, and it also eliminates duplication. So if a celebrity tweets, we store their tweet in a relational database. So we now have two parallel systems. We have the relational database for storing tweets from celebrities. We have the NoSQL database for storing pre-built feeds from everyone else who has, let's say, less than, I don't know, 100,000 followers or less than 1,000 followers. I don't know. You could choose your break-off point wherever you want, experimentally maybe. But this is a great design because it allows a celebrity to tweet and have their data written immediately, right? Because they're going to use a relational design where it just adds one row to a table. And then but it also is scalable for the majority of tweets by quantity are not from celebrities, but from individuals. And we want those to be stored in a accessible and scalable way, although they'll be accessed less frequently. So when I go in and fetch my feed, there actually are now two database actions that have to happen. First, I fetch my pre-built feed, which will include the tweets from mere mortal Twitter users. So from the people I follow who do not have a lot of followers, their tweets will have been copied into my feed in the NoSQL database. But I also have a list of celebrities I'm following. Their tweets will not be in my NoSQL feed because it would have been too costly to copy them there along with all the other million places they need to be. Instead, I do a query to a read replica of the SQL database that stores the celebrity tweets, and I do that, and it does that join to get all of the celebrity tweets for the celebrities that I follow, and then I merge the two, both the NoSQL pre-built feed and the dynamically generated relational database-backed celebrity tweets. Okay? So that's a pretty clever approach, and it's a good example of engineering in a complex system with performance requirements and where there are trade-offs. Often the best solution to a trade-off is to do both, right? That's what Twitter is doing here. For some users, for certain kinds of parts of their system, one system is better than the other. Rather than choosing just one or the other, they've chosen both and combined them, which is pretty cool. All right, so today I talked about both push notifications, which is a totally new service and a new topic, and then I talked a little bit more about a design trade-off with Twitter. So with push notifications, what we saw was that asynchronously sending data back to clients was difficult because clients are not designed to listen all the time. They have private IP addresses. For smartphones, there are push notification services that the mobile OS has built into it that the device will keep a connection to all the time, and then your apps actually have to send notifications through this third party, whether it's Apple or Google, to deliver messages. Web browsers use a slightly different but similar idea that's more managed yourself, which is Websockets. Long polling was the old style way of doing it, same idea. In this case, the web browser client is connected to one machine on your backend, and the service can deliver messages through that bidirectional WebSocket. But the big challenge there is that on the backend service that's requesting the delivery of the message has to find that connection. So your web socket is connected to one machine in the cloud, and that's not necessarily going to be the machine that generates the message that wants to be delivered, right? So often there's a push notification microservice that is responsible for keeping track of where all these connections are and handling the deliveries, and also often those handle both smartphone delivery and WebSocket delivery. Yeah. So with Twitter and with this this trade-off we had was with the relational database had space efficient and fast writes but slow reads. NoSQL databases had these duplicative slow writes but fast reads. And a key insight here was that for some users, reads are more important, and for other users, writes are more important. So if a user is a consumer, like a regular person, they're doing a lot more reading than writing, or even if they're writing a lot, no one's really, it's not what they're writing is not important. Very few people are reading it. So we put their tweets in a NoSQL database, and we duplicate it to all the followers. With celebrities, their writing, their writes are way more important than anyone else's writes in the system. We want those writes to. So in terms of the impact on the system, their writes have a much greater impact on the system than their reads do. That's why I say writes is greater than reads. They may be doing more reading than writing, but their writes, even if they only do a few of them, impact millions of followers. So there's a significant. We need to optimize for celebrities' writes instead of optimizing for their reads, and that points us toward storing their tweets in SQL, which gives us limited capacity. But again, there are only so many of these celebrities, so that works okay. All right. So I hope that gives you the final piece that you need to do homework 5, and also gives you some of what you need for homework 6, although not everything. And please come to office hours if you have questions.